the truck.
Be students, be teachers, be politicians, be preachers.
Cindy's on the move.
Leaders, be astronauts, be champions, be truth seekers. Be students, be teachers, be politicians, be preachers. Be believers, be leaders, be astronauts, be champions.
Yo, he hit 20 feet. That's another $100. Some big heels.
Hello everyone and welcome to Strongman Math Class. Now, that video you just saw was of me at the 2017 Alabama Strongest Man competition pulling a pink fire truck named Cindy. Now that truck pull wasn't actually part of the contest itself, it was just another like a separate sideshow thing for charity. It was for like a breast cancer charity or something. But I didn't really care about that, to be honest. There was a truck there, so obviously I was going to try to pull it. But anyway, for those of you who don't know, I am a strongman competitor. And I had this idea for this Strongman Math Class series, so this video might end up being the first in a series that I might continue if I come up with any more ideas that would be interesting to cover. But for now, what inspired me to make this episode is that so I've been doing strongman for around 3 years now, as of the making of this video. I was watching World's Strongest Man the other night, and they were doing a truck pull event. So here's a picture of that, again, for any non-strongman competitors out there. The typical setup is that they'll have an absurdly large vehicle, like a big truck or multiple trucks or an airplane or a locomotive or some other vehicle that no human being should ever be moving under their own power. And this vehicle is attached to the athlete by a tow strap and harness, and the athlete will have to pull the vehicle a set distance as fast as possible. Usually there's a rope in front for the athlete to grab onto and pull with their arms as well as their legs, as you can see here. Although I've actually done one contest where there wasn't a rope to hold onto and you just had to lean into the strap and drive with your legs. So one thing we're always hearing about this event is that body weight matters a lot, and that the heavier athletes have an advantage over the lighter athletes just by virtue of having more body mass. And you'll hear people say things like, mass moves mass, or so-and-so is one of the smaller guys in this field, so he's got his work cut out for him, or so-and-so has an opportunity to use all that body weight to his advantage. And this just seems to be considered common knowledge in the strongman community. Now, it is true that there is usually a positive correlation between size and strength, which is to say bigger people are usually stronger than smaller people on average, but that's not what we're talking about here. The common wisdom is that, for example, if a 300-pound guy and a 400-pound guy have around the same level of strength, the 400-pound guy should have an advantage in the truck pull event just because of the extra body weight. Now, this seems to be intuitive among strongmen, and everyone just seems to accept it, but I've always been a little skeptical, and I've never actually had anyone explain precisely why extra body weight gives an advantage or prove that it does. Now, why am I skeptical of the common wisdom? Well, consider that the weight of the vehicle being pulled is at a minimum well into the tens of thousands of pounds, at least at the World's Strongest Man level, and the heaviest pulls can be over 100,000 pounds. So it seems to me that the body weight of a several 100-pound human would just be negligible compared to a truck or another vehicle that weighs tens of thousands of pounds. I mean, how much of a difference does it actually make for your body weight to be 1% of the truck's weight as opposed to 0.8%? It just seems to me on the surface that that tiny of a difference shouldn't really matter very much. That being said, I like science, and my intuition doesn't really give a definitive answer to anything. So I decided to do a little math and put the common knowledge to the test a little more scientifically. Contrary to popular belief, some of us can in fact do math beyond using our fingers to count to 10. So welcome to Strongman Math Class, and let's do some science. Now, the first thing to note about this question is something a friend of mine actually pointed out to me after I explained my skepticism of the common knowledge. And what he pointed out was that we're actually not interested in the total weight of the truck. What we're interested in is the force required to move the truck, which is related to the gross weight but not the same. I mean, if it took 50,000 pounds of force to move a 50,000 pound airplane, no human being would ever be able to do it, because humans just aren't capable of generating that much force with just their arms and legs, not even Brian Shaw. So if we want to make this truck roll, we need to apply a force in this direction, parallel to the ground, and that force has to be enough to overcome the truck's inertia, as well as any friction that exists between any moving parts like the axles and wheels. Now, figuring out how much force it takes to overcome that inertia and friction could be really complicated and would be highly specific to any particular vehicle, since it would depend on how many wheels the vehicle has, what kind of axles and bearings and wheels it has, what surface it's rolling on, how much air is in the tires, etc., etc. So we're going to set that aside for the moment, because I think it'll be easier to attack this problem from a different angle, but keep it in mind and we'll come back to it. Now, what we're going to do is first calculate how much force an athlete of any given weight can apply just by leaning against the toe strap without actually putting any effort into pulling. Then we'll come back and compare that to some estimates of the force needed to move a truck. And the difference should give us an idea of how much extra force the athlete needs to generate with their muscles. If that extra force needed decreases significantly as body weight increases, then we'll know that extra body weight really does give an advantage, and we'll have a pretty good idea of exactly how much of an advantage it gives. By the way, I'm doing this in freedom units because, let's be honest, no one really knows what kilograms are. I don't think they're even real. I think kilograms were invented by communists to allow people to tell you how much weight they lifted without actually telling you how much weight they lifted. Anyway, here we go. I'm going to throw up some diagrams and equations, and I'll go through this math kind of quick because I'm sure most people's eyes will just glaze over. And in fact, if you would rather skip the math and get right to the answer, you can skip ahead to the time code on your screen right now. But I will show all of my math on screen for anyone out there who is mathematically inclined. So feel free to pause the video at any time and check my work and let me know if I made a mistake somewhere. First of all, let's go over a few assumptions I made to get this math started. First assumption is that the athlete's center of gravity is at 57% of the athlete's height. Now, in real life, a human center of gravity moves all over the place as the person moves, but that's way more complicated than we need to get for this, so I'm just picking a location. Why 57%? Well, I found some random website that said on average a human's center of gravity is located vertically at about 57% of their height. Was that a reliable source? Probably not, but this is a YouTube video and not a master's thesis, so I can do that. And any number I pick is bound to be arbitrary anyway, so I'm going with this one. And it's close enough, I just need an approximate location anyway. Assumption number 2 is that the toe strap is attached to the athlete at the athlete's center of gravity. This is just going to make the math simpler because we don't have to worry about moments and all that crap. Ain't nobody got time for that. Next assumption, we're treating the athlete as a rigid body. Basically all that means is that we're not taking into account any motion or bending of the athlete's body. We're just pretending you could replace the athlete with like a steel beam or something of the same weight and letting it lean against the strap. Next, we're assuming no slippage between the athlete's shoes and the ground. Again, this is just going to simplify things. And lastly, we're assuming the surface we're pulling on is level. Now here's a diagram of our setup, not to scale obviously. We got the truck and the athlete leaning against the toe strap. Let's go over a few of these variables. Here's the height of the toe strap at the truck, length of the strap, height of the athlete, location of the athlete's center of gravity, which is 57% of his height, as I said before. Then we have two different angles. This one, theta S, is the angle of the toe strap relative to the horizontal, and theta A is the athlete's body lean angle. Now all these are parameters that we can kind of play with to see how they affect things, but what we're really interested in is these three values, which are the forces acting on the athlete and the truck. And here's a simplified diagram of just the forces involved. So T is the tension on the toe strap, and that's the same tension here at the truck and here at the athlete's harness. WA is the athlete's body weight, and FR is the reactive force of the ground against the athlete's feet. Just think of that as the ground pushing up against the athlete and the friction between shoes and ground stopping him from sliding backwards. Since we assume that the strap is attached at the athlete's center of gravity, all three of these forces act through the CG, and we don't have to worry about any moments. And again, you can see the angles here, theta S being the angle of the strap to the horizontal, and theta A being the athlete's body lean. We already know WA because we can plug in different values for that to find out how it affects the outcome. And ultimately, we want to find T because that tension is going to be the force that actually pulls the truck forward. Or actually, we want to find the X component of T because we don't care about any part of the force that's trying to lift the truck off the ground. That's technically true, but in our case, this angle theta S is going to be small enough that T and the X component of T are going to be basically the same number. So I'm just going to use T because it'll be close enough. And to find T, we're also going to need to find FR. Now, to figure out how much force the athlete can apply just by leaning against the strap, we're going to make everything motionless, meaning there's no acceleration, which means these forces sum to zero in both the X and the Y directions. So by doing that, we get these two equations. We know theta A, we don't know theta S yet, but we will in a second. And we know WA, and we want to find FR and T. Two equations and two unknowns, we can solve this. First, we need to get theta S, and to do that, we need to look at these distances. Here's LS and HT again, and also a new value I'm calling HCG, which is the height of the athlete's center of gravity, which is also the attachment point of the strap. So from all this, we can derive this equation for theta S. We know HT and LS, but we still need to know HCG. And here's how I found that. Here's the athlete's height, HA, and 57% of that, which is the location of his CG. Theta A, which is his body lean. And we can come up with this equation for HCG. We'll plug that back into the theta S equation, and then finally we can take this value for theta S and put it back into the main two equations and solve for FR and T. Now, I've just done some algebra magic to rearrange these so I can put them in a computer. Feel free to check me if you want, but the point is, now I have a computer program where I can put in whatever numbers I want for these 5 values and see how they affect this tension force. Now, before I actually did this math, I had a bunch of ideas of how I could play around with the length of the strap and the height of the attachment to the truck and the athlete's height and see if those make any difference. But after actually doing the math, it turns out those 3 values have basically no effect on anything within reasonable limits. So, for example, you can change the height of the strap's attachment to the truck anywhere from 6 inches off the ground to 4 feet. You can make the length of the strap anywhere from 10 feet to 20 feet, or you can make the athlete anywhere from 4 feet to 8 feet tall, and all that pretty much has no effect on what the tension ends up being. So as it turns out, I could have just made this a lot easier on myself and made the math a lot simpler just by assuming the strap is horizontal, but I'm in a sport where we do manual labor for fun, so I guess you could say we don't like to make things easier on ourselves. But since these variables don't really affect anything, I'm just going to pick some arbitrary values for them. So we're going to say the attachment point is 24 inches off the ground, the strap is 15 feet long, and the athlete is 6 feet tall. So with that in mind, let's look at some results. For body weights to check, I used the Strongman Corporation weight classes, so 150, 175, 200, 231, 265, and 300, and then just kept going in 50-pound increments up to 450. So 350, 400, 450, and that's so we can check what these numbers mean for the monsters that compete at World's Strongest Man. First, I checked it for a body lean angle of 45 degrees, which seems pretty reasonable. And you can see here that with this body lean, the tension on the strap ends up being almost exactly the same as the athlete's body weight, and we get a linear relationship between body weight and strap tension, which makes sense. Tension goes up proportionally to the athlete's body weight. So if we change the lean angle to 40 degrees, we still get a linear relationship, but now the tension is actually greater than the athlete's body weight. Same with a 35-degree angle, and even more so with a 30-degree angle. So if we plot all of these on the same graph, we can see that as the body lean angle decreases, which is to say as you get lower to the ground, not only does the tension on the strap go up, but the slope of these lines increases as well. And what that means is that for lower body angles, body weight makes a bigger difference than it does for higher angles. At a 45-degree angle, For every pound of extra body weight, you get pretty much 1 extra pound of tension. But down here at a 30-degree angle, you're getting over 1.7 extra pounds of tension per pound of body weight. So the obvious lesson here is something that I'm pretty sure we all knew already. The lower you can be to the ground in a truck pull, the better off you are. Now obviously this is assuming an ideal world where there's no slippage between shoes and ground, but in the real world your shoes could slip, so there's going to be a limit to how low you can actually get. But generally speaking, the lower you can get without having your shoes slip on the ground, the better off you are. So now we have some numbers for the force that an athlete can apply to the truck just by leaning against the toe strap. But what does this actually mean for the truck pull itself? Well, that depends on how much force it takes to move the truck. We'll call that force FP for pull force, and this is where we'll go back to those estimates of how much force it takes to actually move the truck. So remember I said before that this pull force needs to overcome the truck's inertia plus any friction that's stopping the truck from moving. More math is coming up now, so if you want to skip it and get straight to the answer, you can skip to the time code on your screen now. For anyone who's still here, the inertia part is easy, and we'll get to that in a second, but the friction is complicated because it depends on so many different things like the number and type of axles and wheels, air in the tires, etc., all that stuff I was talking about before. But it turns out we can use a single number to give us a rough approximate representation of all those things and simplify the problem. And that value is C, the coefficient of rolling resistance, which is a measure of how much resistance to being rolled a wheeled vehicle has. I'm going to use a C value of 0.02, and just like the center of gravity location, that's just a number I found on a random website somewhere for a rolling resistance coefficient, so we're just going to use it for the sake of simplicity since it seems pretty reasonable. Now here's a diagram of the forces acting on the truck as it's pulled. FP again is the pull force, which we want to find, and little f is the friction holding the truck back. And here's where that C value comes in. The friction is equal to the rolling resistance coefficient, C, times the weight of the truck, WT. Then we can sum these forces in the x direction and we get this equation according to Newton's second law of motion. This term, m times a, you can think of as representing the truck's inertia. M is the mass of the truck and a is the acceleration created by the pulling. Now we solve this equation for FP since that's what we want to find, and again I have an equation I can put into a computer program. Now we have a number for C. WT is the weight of the truck, M is the mass of the truck in this weird unit called slugs, which is just the weight divided by the Earth's gravitational constant, which is about 32.2 feet per second squared. Now what to do about A, the acceleration? This is another value we're just going to have to pick a number for, use the same value for some different body weights and see how the results compare. To pick a reasonable number for the acceleration, I've taken into account a typical length of a pull for a strongman event, 50 feet, and considered the speed required to finish that course in 50 seconds, a little under a minute, which would be a pretty reasonable speed for an athlete to reach on this event. You've probably already guessed that that speed is 1 foot per second. Now the truck is sitting still at the start, so it's going to take some amount of time to accelerate up to that 1 foot per second speed. So let's say it takes about 5 seconds for the truck to go from a standstill to 1 foot per second. That gives us an acceleration of 0.2 feet per second, or 0.2 feet per second squared, and we'll use that number for the acceleration in this equation. Now we can break FP down further into two numbers, T and what I'm going to call FM. T is what we calculated before. That's the tension placed on the strap just by the athlete leaning against it without pulling. Then the athlete is going to need to apply some amount of additional force with their muscles in order to give the truck that 0.2 feet per second acceleration. And I'm going to call that extra force FM. We really want to know FM, so we can solve this equation for FM, and now we're ready to look at some data. By the way, I'm going to assume 45 degrees of body lean for all of the following plots. Since we want to know how much easier extra body weight makes the truck pull, we're interested in how FM changes with body weight. So let's start with a truck that would be way too light for World's Strongest Man at 10,000 pounds, and you can easily see why a truck of this weight would be too light for Worlds. You can see that once we get up to 265 pounds body weight, we see some negative numbers here for the force required to pull the truck. And what that means is that an athlete at these body weights can give this truck an acceleration of greater than 0.2 feet per second squared just by leaning against the strap. they don't even have to pull at all because the force they apply just by leaning is already more than enough to get the truck moving. And because that's the case, any extra force they do apply by pulling will just make the truck go faster and faster. So these guys would clearly have a big advantage over this poor guy who still has to do another 112 pounds of pulling to achieve that 0.2 foot per second acceleration. Now, like I said, this would be way too light of a truck for world's level competition, but I wanted to show it because it does demonstrate that body weight actually can be a significant advantage, at least with a light truck. But we want to know how this affects world's level competitions, where pretty much everyone weighs at least 300 pounds, and the trucks are a lot heavier than this. So let's look at some heavier truck weights. Here's the same data for a truck weight of 20,000 pounds. Now all the numbers for force required are positive, which means none of these guys can get the truck to 0.2 feet per second squared just by leaning. But still, this 450 pound guy, which is pretty much a guy like Brian Shaw, only has to apply 74 pounds of extra force as opposed to 174 pounds for a 350 pound guy. That's a 57% reduction in force required to reach the same acceleration for a body weight increase of 100 pounds. But this truck is still on the lighter side for worlds, and 174 pounds is peanuts for any world's level athlete, so let's look at a 30,000 pound truck. Now for any weight of truck, we're seeing about a 1 pound reduction in force required per pound of extra body weight. And that makes sense because remember, when we looked at that plot of the strap tension, we saw that for a 45-degree body lean angle, we were getting about 1 pound increase in tension per pound of body weight. So for a 100 pound increase in body weight, we should always see about a 100 pound decrease in force required. The question is, how significant of a difference is that? Well, that depends on the weight of the truck, and we will see that as the truck's weight increases, that difference will become less significant. So for this 30,000 pound truck, we still see the same 100 pound reduction in force required for a 450 pound guy as opposed to a 350 pound guy, but now that 100 pound reduction is only about a 23% reduction instead of a 57% reduction like it was for the 20,000 pound truck. And we'll see that percentage go down again if we look at a 40,000 pound truck. Here we're still getting the same reduction in poundage, but now it's only a 14% reduction. And now we're also seeing some weights that would actually be significant to world's guys at almost 700 pounds. One more plot for a 50,000 pound truck, and now the 100 pound reduction in force required from a 350 to a 450 guy is only about 10%, and this would keep going down for heavier and heavier trucks. So here's all that information on one plot. Now, what's the bottom line? Does body weight actually make a difference on the truck pull? And the answer is, well, it depends. We made a lot of assumptions here to do this math, and it's possible that some of those assumptions don't always hold true. We also picked some fairly arbitrary values for a few variables, and those values could change from event to event. For example, a big one would be that coefficient of rolling resistance that we just plugged in 0.02 for. If we used a different vehicle with different wheels on a different surface, that value could change quite a bit. So these numbers could change a lot, but I think there are a few general rules that we can take away from this. First, the force you need to create with your muscles to achieve a certain acceleration absolutely does decrease with extra body weight. How many pounds that force decreases by depends on your body lean angle, and lower angles are generally better. The significance of that force reduction depends on the weight of the vehicle being pulled. The heavier the athletes and the vehicle being pulled, the less significant the reduction in poundage becomes. So now that I've done a completely unnecessary amount of work to figure all this out, it's your turn. Let me know if there's something I missed, if any assumptions I've made were bad assumptions, or if I've made any mistakes in my math or anything like that. Also, if you want, try changing some of the parameters like that rolling resistance coefficient and see how that affects things, and let me know what you come up with. Lastly, let me know if there's anything else about the sport of strongman that you'd be interested to see covered mathematically like this. I don't really have any more ideas for this series at the moment, but if I come up with some, this could become a regular thing, so send me your ideas. Thanks for watching, and I'll see you next time. If you like this show, there are many ways you can support it. You can talk about it on your own blog or podcast, you can share it on social media with your friends, or you can leave a rating or review on iTunes, Stitcher, or wherever you happen to listen to it. If you're watching on YouTube, you can subscribe to the channel and hit the thumbs up button if you like this video. Thank you for your support, and we'll see you next time on Philosophication.